Log on, tune in, find out. Another good idea from Cambridge.
All right, so I start from where I ended last lecture. So to remind you, now we have the model of our Green's function. Okay, so we have this random travel time correction, which is slightly more complicated because now, of course, we don't have a plane wave. But the analysis is basically the same, slightly more complicated. And so what do we know now about this random phase? We know that this is a Gaussian process. We know it means 0. And we know it's autocorrelation, which is given
Lilia,
here.
the microphone. I still have the microphone.
That's okay, you can.
I think it's for.
I think everybody heard me,
But I think it's for the video recording.
Okay. So, all right. So this is just a recap. So we have the random travel time model. These are the random fluctuations. Here you see that this is for general points, of course. But of course, under our assumption and under our geometry assumption, we have the unknown source, which sits on the range axis with these coordinates, and we need this Green's function at the receivers, which live on the plane of 0 range. And so I call this function mu evaluated this way. I call it mu here, and then we know that this is a mean 0 Gaussian process with this correlation, and this tau mu quantifies the variance, so the strength of these fluctuations of the wavefront. So you recognize they are the same kind of quantities that I had before. And this autocorrelation, it takes this particular form. So this C comes this way just because, so in general, you have some other expression. So this particular expression comes from the fact that I assumed that my original process had this Gaussian correlation, okay? So that's convenient for calculations. Okay, so the original process wasn't Gaussian, just the correlation function has this Gaussian expression. Okay, so now with this model in mind, we can analyze what we need. So we have two imaging functions to analyze, and what we need to do, so for the imaging purpose, we really need to study two things. So the first thing is to study the mean, the statistical mean of these imaging functions, which are random functions. And by looking at the mean, we can infer what is the expected focusing of these imaging functions, right? So if you, if the mean of these functions doesn't focus around the point y star where the source is, then this imaging function is going to be no good. So that's the smallest limit, the smallest thing that we can require of a method. But then, of course, the other thing is, since these are random processes, in order for this to be useful in imaging, we also want to make sure that what we actually observe, so all the realizations of these functions, okay, the random realizations, we want them to be close to the mean. So what that means is that if you look at the variance of these guys have to be small. So in other words, the way to quantify that is we can actually compute signal-to-noise ratio, which is defined here. So what we want is that this be high, so that is if we compare the mean, so what we expect at the point of focus, you will see that the means will actually, of course, focus at the right place. So if we look at the peak value of the mean, and then we compare that with the standard deviation around that point, we want this to be as large as possible in order to be able to actually obtain something that is, useful. Okay, so that's what we need to do. Now, how do we compute these means? Well, so all this work that we have done, we see that, our model is really, if you remember, so the Green's function now is just the Green's function in the homogeneous medium times e to the I omega times mu. So that's the random process. So the only random part is in the phase. And now, and since we know that the phase is Gaussian, then we know how to compute the moments. So this is how the moments are computed. So it's very easy to check. So just take a a Gaussian variable. To compute, this is what is known as the characteristic function. So if you compute, let's say, so this is integral of e to the I omega u, e to the minus omega u squared over 2 sigma squared of what I call the tau nu squared over square root of 2 pi tau mu. And then integrate, and you're going to get exactly that formula. So that's for the mean. And also sums or linear combinations of Gaussian processes. So this is also a Gaussian process. So this is how the mean looks like. Okay, so that's why by doing these sort of averaging techniques, we learn now that we are dealing with Gaussian processes, and these are nice because we can compute everything explicitly. So here is how the result looks like. So if you look at the mean of this, then this is the expectation of, well, like I said here. So you have expectation of minus omega mu squared, and that's omega tau mu, right? So this is, so what it says is that if you have a random process, so if you have a random phase like that, when you take the mean, you get decay, okay? And remember that we are interested in the case where we have large fluctuations of the wavefront. So we are looking at the case omega tau mu much bigger than 1. So what this says is that if we look at the mean field, or what we call the coherent field, this is what standard imaging techniques rely on, we see that this is going to be almost 0. Okay, so that's typical of the case of waves in random media. When the waves go long enough distances, basically the coherent field is gone. Now, however, let us look at these kinds of moments. Okay, so here you see I'm dealing with differences. So I take differences of phases like that, and then I just do the computation. I use the formula that I had on the previous slide, and this is what I get. So now, if you look at this expression, remember that omega tau mu is big, right? So you see that this guy is going to be essentially 0 unless x minus x prime over L is close enough to 0. Okay, because then C at 0 is 1. Of course, that's the autocorrelation. And so then you can expand this around x minus x prime over L is equal to 0, and then you obtain this formula. So this formula is actually quite an amazing formula, because turns out that you can derive this formula using all kinds of models. So what this formula says is the following, that if you look at moments of this form, so G times G conjugate, okay, what you get is that is what you would get in the homogeneous medium. And then you have this decay. Okay, so this moment formula, we have derived this moment formula over and over using different types of models, much more complicated than this one, going through PDEs, through stochastic PDEs, and so on, and it's always coming out like that. Okay, so it looks like it's a sort of like a generic formula. And what this formula is saying is the following. So this is actually telling us how things decorrelate. Okay. So now, if omega is the same as omega prime and mu is the same as mu, if x is also the same as x prime, then of course what you do is you just computing intensity of the Green's function, and this exponential factor is just 1. However, as you look at these guys for different frequencies, omega and omega prime, and different x and x prime, you see this decay, and this is basically telling you how these two random functions decorrelate. Okay, so for omega minus omega prime, much bigger than omega d, than this parameter, which is 1 over tau mu in our case, then essentially this guy is going to be essentially 0. Okay, so it just says, that these two fields have nothing in common. Okay, and the same for xd. So these guys, omega d and xd, are called the decoherence length and frequency, and they are determined by the statistics of the fluctuations in this simple case that I discussed here, they are determined this way in terms of this parameter p mu. Okay, so so here is what this says. So using these results, you can see that if you look at the expected field, so this is the coherent field, then this guy is going to be essentially 0 because of this exponential damping. But if you look at its variance, okay, because this one is not 0, so the second moments are not 0, if you look at the variance, then you see that the variance is large. So what does that mean is that at this long distance of propagation, the field is essentially incoherent. Okay, so it looks like noise. Okay, so let's study the Kirchhoff migration function. So this is a Kirchhoff migration function with the model of the data that I reminded you. Now, we can take expectations, use those moment formulas that I said over there, and this is to compute the variance, you compute the second moment. Okay, so these are exactly the formulas that I had before. Now, we would like to analyze this further, and so what we do is now we put in the expression of the Green's functions, and I'm going to make some simplifications on the geometry, again, in order to get rather straightforward results. So there is some assumption on the pulse width, so I'm going to be in a regime where the bandwidth is much smaller than the central frequency, so that makes the calculations convenient. I am going to be in a regime that has what you call a large Fresnel number. So that basically means that if you look at the aperture, this is much bigger than this ratio here. You will see that this is a very important ratio in imaging. You will see that this characterizes the focus resolution in cross range. Okay? And I also have this assumption here so that I make my life easy. So basically, all these assumptions together allow me to make this following approximation of the phases. Okay, so I have omega times the travel times. This is the travel time in the homogeneous medium. Okay, so all I really did here is I scaled things just so I could approximate. So omega tau is omega over C naught square root of L squared plus XR squared. Okay, so all I did is I made all these scaling assumptions so I can make this approximation, okay, for the travel time between. Okay, it's just simple analysis. So this is what is called the Fraunhofer regime. And then, okay, so that's, so using that approximation, this is really the model of the data that I have now with this scaling assumption, scaling geometry assumption. So this is the model of the array data for the passive array. This is for the active array where you go from the source to the scatterer and then back. Okay, so it just looks the same. I just approximated the travel times like so. Okay. So now we also need to make some scaling assumption on the points at which we form the image. And this again, what I'm going to do, I'm going to make all the scaling assumptions such that I can approximate the travel, the phase that takes me from the receiver to the point y at which I evaluate the image this way. Okay, so it's just sort of choice of the search domain and so on. So this is rather straightforward. And so when you do that, then you obtain, so you substitute all these things into the expression of the imaging functions, and then you obtain that the Kirchhoff migration function is this one. It is a random function because of this random phase. Okay? Now, we can compute its mean. The mean is this one. It's given over here. So if you look here, so what's happening? So you see you have this strong damping. You have this strong damping here. Okay? And then if you look at the integral over the array, which is the one here, so this integral over the array, it's the one that gives us the focusing of the image in the cross-range direction. So this integral, you see, I arranged everything so I can compute everything explicitly. And so this integral is this one. It gives you this sinc function, so that's a sine of x over x function. So this is the sinc function. And basically what we define as resolution is the distance between the peak of this function, which is at c is equal to 0, which means cross-range offset from the source equal to 0. So that means that the peak is at the correct cross-range, which is where the source is, at c is equal to 0. And the resolution is the distance from that peak to the first 0 of this sinc function. So that's how this is defined. So this is the cross-range resolution that I mentioned. And then you have the range resolution that comes from this integral. Okay, but what is really, really important here is to note that, yes, this focus is in the right place. So you can show that this focus is in the right place. Also, you know that at eta is equal to 0, you're going to get a peak. But the peak is exponentially damped because of that. Okay. So now you can also, so that's basically what this says. Okay, so I have an image that looks basically almost the same as if I didn't have the random medium, except that the peak is exponentially damped like that. Okay, and remember that I'm in a regime where omega tau mu is large, so that is really, really small number. Okay, so now I compute the variance, and the variance doesn't decay. Okay, and so if I look at the signal-to-noise ratio of the Kirchhoff migration function, I see that, I have this factor, so this as well, okay, you can improve this a little bit by increasing the aperture and so on. But really, these are not really important because no matter what you do, you have this d here, which is the exponential damping, and no matter what you do, you cannot get rid of it. Okay, so that says that this imaging function has very low signal-to-noise ratio. So in other words, you are going to see results that are not reliable. So I'm going to show you now simulations of how this is actually doing. So now these are not honest solutions of the wave equation with the finite element methods. This is what I showed last time. Remember that now we want to study this random travel time model, right? So here I'm afraid you can't see very well. So this is the wavefront over a large aperture. This is sort of a smaller version of that. So here is how the traces look like using this random travel time model. Here is where you don't have any fluctuations. So you see this nice sort of hyperbolic thing. And then when you have the fluctuations, you see some wavefront distortion. Okay? And here we show some images. So first of all, here, this is the mean, the expectation of the Kirchhoff migration function. You see it peaks in the right location where the source is. The mean is right where it should be. And then you can actually measure the resolution, and you see that is exactly what the theory says. But so the standard deviation so here is an example of, for a particular strength of the fluctuations, you find this is the mean. This is the standard deviation calculated at the peak. So if you look at the signal-to-noise ratio, it is very small. And so what you actually see in the simulation in this case is exactly this. So if you compute the image in different realizations of the random medium, what you're actually seeing is that this image, sometimes it doesn't focus so well, but even if it focuses, the peak of this sort of dances around. Okay? So this image does not look at all like the image I showed you before, because that one came out of data computed from solving the wave equation. So there was all that signal that came before and after the coherent stuff, right? So that was the coda. So this model doesn't capture that. So the only thing that this model is going to give you is sort of dancing around of the peak. Okay? So this is going to dance around, and on the average, when you take the average of this, you are going to get something that on the average is focused here, but it's very small. Okay? That's what this is saying. Okay, so now, this was for the passive arrays. For the active arrays, goes the same way, but it's much more complicated because you have two phases and so on. Now let's look at coherent interferometry. So the coherent interferometric function is now quadratic in the data, okay? And you already see why this is such a good idea, because remember that, So the Kirchhoff migration function was linear in the data, okay? So it was really contained terms like this. The random terms were e to the I omega mu. So when I take expectation of this, I get something that goes down, right? It's really small. Now when I do the coherent interferometric method, I'm dealing with things like this, G bar, okay? Well, these are much better things because you see, I'm sort of subtracting phases. So this one has a random phase, this one has a random phase, but when but in this quantity, I subtract the phase from this phase, I subtract the phase of that one, right? And when I do that, apparently something good is happening because when I'm computing the mean of this, I don't get something that decays the same way, right? So at least this one has a chance to make it. So that's what, you know, if you heard in the very beginning when George Papanicolaou was presenting the time reversal method and so on, he was preaching, that's what he was saying. It's G bar. So that's what this is really saying, okay? So, okay, so using the same kinds of things. So now for convenience, again, for the computations that I'm going to present, well, very briefly, I just tell you how I do them because obviously I'm running out of time. So this could be any window functions, okay? So remember that the coherent interferometric method is quadratic in the data, but I'm making sure that I'm taking sort of these cross correlations at frequencies that are not too far apart, and that comes from the fact that I have this loss, this decorrelation there, so that's really where that came from. And also I make sure that I'm taking points in the array at which I do cross correlations that are not too far apart, because if they are too far apart, then the things are not correlated and therefore I'm not achieving anything. Okay, so that's the idea. And so these window functions can be any functions, but for the calculations it turns out that it's useful, I mean, simpler to consider Gaussians again, because everything is easy to integrate if it's Gaussians. Okay, so how do we analyze the imaging function? So it turns out that there is a very, very useful tool in this context, which is called the Wigner transform. So this is a very, very useful tool for studying sort of the wave field at high frequencies in random media. Okay, so the Wigner transform is defined here. So you see, what you do is you take your random field P and you and using that, you define this sort of, so what is this is like you take Fourier transform in the offset of the frequencies and in the offset of the sensor location. Okay, so this is the definition of the Wigner transform. And so now, if you take this Wigner transform, okay, and you write the product P bar as the inverse Fourier transform, okay, so you write this in terms of the Wigner transform. And then you plug that in the expression of the coherent interferometry. And you use these geometrical assumptions that allow you to simplify the travel times the way I told you. Okay. And then you do the calculations. Okay, there is nothing else. That's all I said, you know, and now it's algebra. You do the calculations. And when you do that, you find this remarkable expression, which says that the coherent interferometric method is nothing else but the Wigner transform smoothed over all its arguments, okay? And the smoothing is done by integration over the array, integration over the frequency, okay? So these are the variables omega and x. So here, really, I mean, one way, actually, I should have said, one way of thinking of this Wigner transform that I think is very useful, you can think of it as intensity of the waves resolved locally around the frequency omega and location x. So it's resolved over directions. So this kappa here is a vector that you can write it as, so you can write this kappa, it's useful to think of this like that. So omega over C naught, which is the wave number, times another vector q. So now this vector q has no dimension. And the meaning of this is like a direction. So in other words, if you look here, it's useful to think of this as energy resolved locally around frequency omega, location x, over plane wave directions, which will be q, and over time, t. Okay? So what the coherent interferometric method turns out to be is nothing else but the Wigner transform smoothed by integration over the bandwidth. Yeah, here I should have had over the bandwidth, sorry. It's not from minus infinity to infinity. That's wishful thinking. So over the array, now I have integration over directions, over plane wave directions. Remember, kappa is really determined like that. And integration over time. And this integration is over the windows that are used in the expression of and the size of these windows is determined by this parameter, by this omega and x, which is what I chose before. Okay? So that's the expression. So now, why is this useful? Well, it is useful because now there are techniques to analyze the Wigner transform. In this case, of course, it's much easier than others, but there are ways to do that in much more general context. So, but in our case, let's look at what the Wigner transform looks like, okay? So all I did is I plugged in the random travel time model, and I ended up with this sort of complicated expression. And so if you look at the phases in this expression, you see what I have here. So I introduced this notation. So I'm dealing with averages of travel times. I'm dealing with differences of travel times, averages of these random phases, and difference of random phases. So I don't know about you, but when you look at this expression, I myself, when I look at it, I say, God, if I could just linearize in x tilde, right? If I could just approximate this. Of course, that's not quite good because you can't really do it here because x tilde lives over your whole Rn. However, remember, we don't really need the Wigner transform. We need the smoothed Wigner transform. So in particular, if I look at the Wigner transform, smoothed over directions by integration over the support of my window, and what I did here, right, so I had this window here, psi hat. But remember that I said that I'm going to use Gaussian window, so I make it simple. So if I put the Gaussian window there, I get this expression. Okay? So that's what it is. So that's just the smoothed Wigner transform by integration over the support of that window. Now, when I evaluate the integral over kappa, okay, I get this guy. So this guy, what it tells me is that, well, you might integrate in the Wigner transform over all the x tilde over the whole space, but really, only x tilde of the order capital X, which is the parameter that determines the support of the window, is going to make a difference. Okay? So using that argument and then looking carefully at the scaling, you can actually make approximations of all these guys here, okay? And then again, happily do the algebra. And then you obtain this really interesting expression, I think. So this is the Wigner transform smoothed over directions, and this is the expression it takes, assuming the Gaussian windows. And so this expression, it's interesting. Why? Because if you see really, so this Wigner transform, what it is? Well, it is a function that peaks in somehow, you think, in the vicinity of, okay, so suppose for a moment that I didn't have fluctuations, right? So you could do this calculation of the Wigner transform in the homogeneous medium. And what you will find an expression that is basically the same, except that you wouldn't have these terms that involve the mu. So what will this expression mean? So the Wigner transform will be something that is peaked at xi is equal to 0, right? Because so suppose that this is not right. So this is peaked at xi is equal to 0. And this is also peaked at time t, which is equal to the travel time. Okay? Now, if you have the random medium, here is what you get. So what you get is that, the location of the peak of this Wigner transform is now randomly fluctuating. So the peak in time is going to be shifted by this random phase mu, okay? And the peak in C is going to be shifted by this guy, which, you know, is the gradient of this random process. Here I assume, of course, that this random process is smooth in X. And so what this is actually showing you rather explicitly is what we call the peak dancing. Okay, so this is just sort of dancing around, is changing with the realizations. Okay, and so now what you do is you can compute using the expression of the Wigner transform. Now you can compute moments, and this is the expression of the expectation of the coherent interferometric function. And you see, it looks rather complicated, but, well, it's just Gaussian in all directions, because everything was Gaussian for me. And what you find is that, yes, this function indeed peaks in the right location. So it's going to peak when the offset in cross range and the offset in range are 0. And now these terms here are going to determine the range resolution and the cross range resolution. Okay? So here is, let's look at the range resolution. So the range resolution is essentially given by this guy, right? So this is the standard deviation of this Gaussian here. Okay? So this is how it looks like. And if you look at this carefully, so now you can try to analyze what is the effect of the parameter omega that you chose to determine the size of the windows that we used in the coherent interferometric method. So you can see now by how you should choose omega in order to improve the focus, for example. And when you analyze this carefully, it's rather well, I mean, I just don't have time to do it, but it's not difficult to do. So you can just you have this explicit expression, and you can try to see what happens if you choose omega, let's say, much bigger than omega d. So what does it mean, omega much bigger than omega d? Here. So if omega is much bigger than omega d, it means that I'm going to let frequency offsets to be much, much bigger than the decoherence frequency, which is what I got over there, right? So in particular, I could let omega go to infinity, so therefore I will have no window, really. Okay? So you can try to see what happens, and then you find, amazingly, that that's not going to improve your focus. Okay? Now, however, you will see that if you do that, you are going to decrease the signal-to-noise ratio. Okay? So choosing omega much bigger than omega d turns out not to be such a good idea. Now, what if you choose omega much smaller than omega d? Well, then you can show, looking at this expression, that what you get is that the range resolution now becomes like C naught divided by omega. In the homogeneous medium, the range resolution is C naught over the bandwidth. Okay, so now if I choose omega really, really small, now I'm losing range resolution. Okay, so I'm going to get blur in range. So it turns out that by just looking at this, you find that the optimal choice is that you should choose omega to be of the same size as omega d, which is the decoherence frequency. And that seems to be the best balance. Okay. The same discussion applies. So the same discussion applies to the cross-range resolution. Okay? So the cross-range resolution, the formula that I have there is, now, again, I have another Gaussian in C. So I look at the standard deviation of that Gaussian. That determines the focusing. And that's written there explicitly. Remember that in the homogeneous medium, or the expectation of Kirchhoff migration, the cross-range resolution was lambda 0 L over A. Now we have this factor, okay? And again, you see, what do you achieve? Well, again, you can see that if x much bigger than xd, you are not going to achieve much in terms of resolution, because you see here is much easier to see than previously. When x is much bigger than xd, then this guy is going to be very small with respect to that guy, right? So you can just forget about that. However, when x is much smaller than xd, then this one is going to dominate, and you are going to get too much blur. So it looks like the best choice is that x is like xd, and then in that case, the cross-range resolution turns out to be like that. So it looks almost like in the homogeneous medium, except that instead of having lambda 0 L over A, you have lambda 0 L over the decoherence length. Okay? And again, these formulas come up from much more sophisticated models. And finally, let's consider the signal-to-noise ratio. Again, this is a rather lengthy calculation, but you now know all the mathematics that goes into it. It's just computing stuff. And so this is the formula of the signal-to-noise ratio. Okay? And just to remind you here a little bit, so the tau mu, so omega d is like 1 over tau mu. Okay, so that's the decoherence frequency. And xd in this kind of model turns out to be proportional to the correlation length. That's in this kind of model. So this expression shows how the signal-to-noise ratio depends on the parameter omega, which determines the size of the window that we used in coherent interferometry. We saw that from the point of focusing, it looks like omega the same as omega d. In other words, omega tau mu is equal to 1 seems to be the right choice. Okay? And now for this guy here, so this one contains this correlation length, and that's where the decoherence length comes into play. Okay? So now, when you look at this expression, you can draw the following conclusions. So you see that, first of all, the signal-to-noise ratio of this method is very different than the one we had for Kirchhoff migration. For Kirchhoff migration, the signal-to-noise ratio was exponentially small. No matter how big the array was, no matter what you did, right? There was no way you could rescue that method. Now, coherent interferometry doesn't have an exponentially small damping, okay? So, moreover, now we can see, and this expression shows explicitly how the choice of the parameters affect the signal-to-noise ratio, okay? And so, if we choose, so we already saw that choosing omega about the same as omega d is the right choice. And so now, if you look at this expression and you let tau mu grow, what does that mean, tau mu grow? It means the effect of the random medium is stronger and stronger. So if you let tau mu grow, this signal-to-noise ratio has a finite limit. It doesn't go to 0, okay, which is kind of nice. And also, you can see that you can improve the signal-to-noise ratio of coherent interferometry by increasing the aperture. And in fact, you can show that the signal-to-noise ratio is going to be large as soon as you have an aperture that is bigger than the decoherence length. Okay? So let me show some results now. So here is a table. So remember, so this is the same parameter that I had before for coherent for Kirchhoff migration. So for this parameter sigma, which is like 10 to the minus 4, then the standard the signal-to-noise ratio for Kirchhoff migration was like ridiculously small, right? Like 0.01 or something like that, very small. Now for coherent interferometry, it's large, okay? And then if you increase the strength of the fluctuations, it's going to stay large. Okay? Of course, we cannot increase too much because we have these assumptions that we made that the travel time model holds, right? So sigma was supposed to be small anyway. And so here is the computed expectation of the Kirchhoff migration. and the computed expectation of the coherent interferometric imaging function with the correct parameters, what the theory says, with omega d, omega is equal to omega d, and x is equal to xd. And what you see, the difference between this one and this one is that this one is a bit blurrier, right? So blurrier but stable. And so here, just sort of to give you an idea of how this means, so here I plot three different the images in three different realizations of the medium. So this is Kirchhoff migration. You see the peak dancing around, and this is coherent interferometry, okay? There is some peak dancing here, but very little, much little, and the reason is because, of course, all the theory holds in asymptotic limit. Everything goes to 0, which is, of course, not the case here. Okay. So, I'm sorry I didn't have time to talk about more complicated model, but what I want to say is that essentially, you know, so I chose this simple random travel time model sort of to convey the important ideas that lie behind this coherent interferometric imaging approach. And these ideas basically say that, you know, if you are in the random medium, when the random medium starts to really affect your data, which means that if you look at the field, the expectation of the wave field becomes really small, then in that case, the traditional methods that work, you know, that are linear in the data field are not good. So you know, so we propose this coherent interferometric method that really borrows from, you know, the whole idea of this method came really from understanding of what this Wigner transform does, okay? So it all boils down to the analysis of the Wigner transform in random media. And I presented a very simple setup where this can be done, but you know, there are much more complicated things, and I would be happy to point you to some of our papers where we did that, and also to other people that did this, okay? And so the idea is that using these techniques, you can really push the imaging field a lot more in terms of, you know, actually being able to compute images in situations where the random medium has a strong effect. And just to remind you what I showed in the previous day, so when you are dealing with data like this, where there is a lot of scattering from the medium, okay, then the Kirchhoff migration methods or traditional methods, whatever methods you like, they are going to use to give unstable, noisy, speckled images, and you know, this method seems to do much better. However, this method breaks too, so we have to be careful, because you see, when you look at this method, so when you look at this data, right, with your eye, you can still make out these wavefronts, right? You can still see them. What does that mean? It means that, yes, there is a lot of fluctuations. So all this stuff that you see here, all this stuff here, those are the fluctuations, okay? So is the coherent, so the coherent field is just this, the wavefront, okay? The stuff is the fluctuations. Now, so this data, yeah, it looks noisy, but still we are in a case where there is still coherence left in the data. That's why you can see this wavefront, right? Now, it turns out that if and you can quantify precisely how long the waves have to go in the random media, so this still happens. So there is this length scale, which is known as the scattering mean free path, and so on, and then it tells you, you know, that you should not go more than 1 or 2 scattering mean free paths in order to still have coherence in the data. Now, what happens if the waves go deeper than that? Then what happens is that these fluctuations are going to become stronger and stronger, and these coherent echoes are going to become fainter and fainter, okay? So, in other words, you know, you can think of this as being a signal to noise ratio, okay? So, here, really, the signal is still strong, but now, if the waves go deeper in the medium, the noise is going to be stronger. So then, this coherent interferometric method, the way I presented it here, well, of course, the random travel time model, forget that. That's not going to apply to this data. But this coherent interferometric method alone is not going to work. So what you need to do is you need to come up with other techniques. So we have started to look now at techniques which are called data filtering techniques. So it turns out that there are ways to take this data and pre-process it. And the purpose of the pre-processing is to remove a lot of the noise that is done there. And you can do that actually using all kinds of techniques, spectral analysis, using random matrix theory, and so on. And, so it's a very hard problem, and, but we have done some cases. And now, if you do such data pre-processing, then the effect of that will be that you are going to enhance the coherent signals. And then, after you have done that, you can use coherent interferometry. Okay. So, I think I ran over time, so I'm sorry. Thank you.
So if you vary that this, if you assume that the clutter, this random somehow structure is varying somehow.
Yes,
spatially,
if it's not stationary.
But yes, could you use this type of methods to use the way how the this clutter varies? Like if you would have the like radar images and you have like forest and then you have a
yes, you can do these kinds of things. And actually there are, there is very little done in three-dimensional media really in this respect. But there is work that has been done in layered media, for example. Yes, you can use all kinds of ideas like this. So actually, Jean-Pierre Fouque and I think Jocelyn Garnier, maybe Knut Zollner, I'm not sure if he was involved in this project. They have done these kinds of techniques actually using time reversal. So what they did is, you send a signal in a layered medium and then you get noise basically looking like. And then what they did, so it turns out that if you take that signal and you take windows of it and then you send it back, because the idea is that, in a particular time window, you are going to get signals that come from a particular depth. And then, so doing this kind of processing, you can infer that. And actually, I have to say, I should have remembered, one of my students, so I actually have a paper on this in layered media. I forgot. So one of my students, Fernando Gonzalez Cueto, that was part of his thesis. Actually, that was the first time we developed a filter of clutter effects for randomly layered media. And with that technique, it's a technique that is actually quite reminiscent of these sort of velocity estimation techniques that Bill Symes has, which is called the differential semblance method. I apologize for those of you that don't know about that, but so it resembles that. And it turns out that you can use these kinds of filters that we developed to find we found the wave speed profile, okay, and which was varying. Now, in terms of estimating statistics, the correlation function and so on, I don't think there's much done. We have done it for waveguides, and I spoke about that last fall in MSRI. But there is, honestly, there is so much work to be done in this area. It's really wide open. So I think it's a very good field for people to go into because, there's plenty of opportunity to do works of all kinds, theoretical and numerical and whatever.
Questions? Let's thank Liliana for this great course.